Great. Well, thank you very much. It's a pleasure to be here. As Paul pointed out, Andy is my thesis advisor. It's always a little sort of an intimidating situation having to get up and give a talk after your thesis advisor, especially doubly in my case, because my thesis advisor is both as unpredictable as he is brilliant. So I had no idea what Andy would really cover. My goal in this talk is to sort of, whoa, that's really bad what just happened there. I'll just fix that. Should never install software. I think this should work now. There we go. Is to give this group sort of a background on what I would think they would need to know about recent thermal results. And the main points I'm going to try to make in my talk are sort of shown here. While, of course, it's lunar ice that we're really interested in, understanding what's going on in terms of temperature is a real key to this, and that temperature can be thought of as sort of a master variable in this whole problem. As Andy described, temperature determines the thermal stability of volatiles. It also determines the spatial distribution of cold traps and their thermal evolution over time. And then temperature can be used to correlate many other data sets that we have that we'll be talking about as the course of the day goes along. And in my talk, I'll be showing some of those correlations and then also come in towards the end of Paul Lucy's talk and talk some about the most recent results we have in terms of correlating temperature with some of the LOLA results. So that's sort of an outline for my talk. So this slide here is sort of a restatement of a slide that Andy showed, which shows the thermal stability of a bunch of volatiles as a function of temperature. And this brings me to one of the first main points I want to make, is that there's a lot of potential ices on the moon, not just water. If we take a particular temperature here of a cold trap, let's say 100 Kelvin, these plots show the sublimation rate in meters per billion years for a wide range of volatiles. If I have a cold trap at 100 Kelvin, it shows that we can keep water stable over billions of years at the surface, which was the original Watson, Murray, and Brown suggestion. But the key thing is that all these other volatiles, that includes organics and inorganic volatiles, will also be stable at this temperature as long as their so-called volatility temperature, i.e., let's say the temperature at which they'd sublimate sort of a millimeter in a billion years, in other words, stable over the life of the solar system, as long as their volatility temperature is higher. So for instance, in a cold trap that's cold enough to trap water ice, we might expect to find a whole range of aromatic hydrocarbons, linear amides, and amines, and all these other types of inorganic compounds, mercury, sulfur, etc., that are less volatile than water. And as you go down the temperature scale here, then you have the possibility of trapping a wide range of other volatile materials too. So this is a very important point, that just based on the basic theory of thermal stability, we would expect that the cold traps on all planets contain not just one dominant water species, water being an important one, but we might expect to find a variety of things, and the data that we're getting suggests that that's in fact the case. I'll skip these. So a lot of what I've been involved with over the last few years has been looking at and understanding the data that we've been getting back from the LRO Lunar Diviner radiometer experiment. LRO now has been orbiting the moon from polar orbit for almost 4 years now. And we've accumulated a very exciting data set that is by far the most detailed and thorough example of the set of measurements of the thermal emission from an airless body. The instrument provides mostly thermal emission from the surface information as well as solar reflectance. And what we have been doing is trying to interpret this in terms of a range of things, like what it means about the thermal properties of the moon, what it means about composition, and also what it means in terms of the stability of volatiles at the lunar polar regions, which was one of the main goals of the entire mission. The thing about temperature, though, is that there aren't too many things about temperature that necessarily provide direct information about volatiles. You need to sort of correlate this type of information with other sorts of data sets to really understand what's going on. But you can learn a lot through temperature, especially in terms of the spatial distribution of potential lunar cold traps. What I'm showing here are going to be, for the north and south polar regions, compilations of diviner measurements of the temperature of the surface. And we'll define more what that means a little bit later. The first set show the annual maximum temperatures in the polar regions. And you can see here that there's quite a wide range. The obliquity of the moon is rather low. The seasonal variations are just confined to the first sort of the region within about 1.5 degrees of the pole. And so surfaces that are tilted towards the equator can become very hot in the polar regions, as much as sort of 350 Kelvin. But surfaces that don't receive direct sunlight can get very cold. And you can see here that there are some places here where the annual maximum temperature never gets above more or less 50 Kelvin. And this was somewhat of a surprise to us when we first got these data from the moon, because we hadn't really had a chance to fully explore what some of these crater shapes could do in terms of cold trap temperatures. The next two slides show the annual minimum temperatures. You can see that the moon can become extremely cold. In certain places, we've measured temperatures down near 20 Kelvin. Again, a little bit exciting. These are temperatures that are in fact colder than the polar caps of Pluto, as we currently understand them, simply because they just are places where the sun hasn't shone for billions of years, and they're just extremely cold. And then another plot, which is annual average temperatures. And you can see here that there are a number of places where the annual average temperatures are less than 100 Kelvin, and this will turn out to be significant from the standpoint of potential water ice cold traps. Now, what can you tell about subsurface temperatures? Well, this is done largely with thermal models, where you basically adjust the parameters to match the observed surface temperatures, and then make assumptions about the subsurface thermal properties. These are some examples from our science paper that are more illustrating the effects of heat flow from the interior, but also illustrate the dependence of temperature variation as a function of depth. So just taking the no heat flow case here, we have a surface that has an annual average temperature of something like 36 Kelvin. The surface temperatures move around quite a bit. And this is another thing about the cold traps that's important. The initial goal of Diviner was to measure the temperatures of the cold traps, but it turns out if you plot these temperatures as a function of time, they go through all sorts of crazy gyrations due to the fact that you have diurnal as well as seasonal temperature variations, as well as large topography, which is constantly moving shadows in and out of these regions. So each of these regions has quite a complicated temperature history as a function of time. And then if you assume sort of standard Apollo soil thermal properties, these temperature fluctuations then damp down as a function of depth. And so by the time you get roughly 2 meters below the surface, you're in a stable situation thermally as a function of time. And then the heat flow then becomes an important parameter in terms of determining the temperature. Now, if you have different thermal properties, i.e. maybe ones of solid ice, then these temperature waves will penetrate quite a bit deeper into the subsurface. And this could be an important parameter in terms of the total depth of the lunar cold traps.
That particular model is for the L-Cross.
Yeah, this is the L-Cross landing site, which is a little out of order because I was going to talk about that next. But just to give you an idea what we're talking about in terms of the depth of these cold traps. Now, what would determine whether, for instance, a volatile like water might be stable there, you can, again, sort of restate these sublimation rates. Here's 1 millimeter loss per year. This is for exposed surface ice, the blue curve here, and you'll see the canonical in 10 to the 9th years at 100 Kelvin. But as Andy pointed out, there could be cold trapping on much shorter time scales, maybe even as short as diurnal time scales. If you look at sort of at 10 microns per year sublimation rates, you can get potentially stable surface ice at temperatures of about 170 Kelvin. So this gives you an idea of sort of the range of cold trapping temperatures that can occur depending on what your frame of reference is in terms of time. And then burying ice below soil layers provides a diffusive barrier, and that will enable you to have ice stable at warmer temperatures than you might have expected if it was at the surface. And this shows for 10 centimeter and 5 meter lag deposits what that effect is. And that effect is on the order of 20 Kelvin as well, of course, subject to uncertainties in terms of our understanding of the diffusive properties of the soil. So the bottom line is that thermal stability provides quite a range of possibilities in terms of where ice could be stashed. Now, we've applied these types of calculations to the thermal state, for instance, of the south polar region of the moon. And this provides a sort of a permafrost map based solely on temperature as to where water ice could be stable in the lunar south polar region. And you see here that the so-called permanently shadowed regions, or PSRs, which are indicated in white here, these are places where you could have thermally stable ice on the surface for billions of years. Surrounding these regions, though, are going to be areas that do receive some sunlight during part of the year, but yet maintain average temperatures that are cold enough that you could allow ground ice to be stable. And this shows where those calculated areas here. Basically, all of these so-called PSRs are surrounded by potentially regions of potential ground ice stability. Typical depths for these, assuming standard lunar soil properties, are on the order of 10 centimeters below the surface. And what we'll see as the short course goes along is that if this were, let's say, Mars, for instance, where you have almost all the water ice niches are filled, there'd be a ton of ice on the moon, and that's not what we see. We have, though, one piece of really exciting ground truth, and that came from the L-Cross impact. L-Cross impacted into Cabeus, into a region of permanent surface ice stability. Turns out to be one of the coldest places on the moon. And this shows a histogram of all of the temperatures in the south polar region of the moon. You can see that there's quite a bit of territory below 100 Kelvin in terms of annual average temperature. This dot here shows where L-Cross ends up on that. And you can see here that thermal stability would in fact predict the stability of quite a number of volatile species, including all these things, SO2, NH3, CH2O, CO2, H2S, water, and then as well as all the less volatile compounds than water, including mercury, sodium, and sulfur. All the ones that I've circled now have been detected either directly or indirectly by various instruments on L-CROSS, LRO, and elsewhere. And so on the basis of at least the L-CROSS experience, the basic concept of, thermal cold trapping and volatile stability seems to work, all right? The issue, though, is, how lucky a strike was this one piece of ground truth that we have at L-CROSS, all right, relative to all the other remote sensing data we have, which suggests that there isn't a lot of ice, at least in the accessible part of the moon to remote sensing. And so this is where things get kind of interesting. I just wanted to touch briefly on this idea of cold trap evolution, because it may be important for some of the things we discussed earlier. With thermal models, we can reproduce many aspects of the observed temperature behavior once we have the topography, which really controls the distribution of sunlight and reflected scattered solar radiation and thermal emission from other surfaces. We've gone through this exercise to sort of calculate how these cold traps now have changed as a function of time. Basically, as the tidal evolution moves the moon away from the Earth, the obliquity of the moon has also decreased as a function of time. So as you go back in time, more of the poles of the moon have been illuminated. And what I'm going to show here are some calculations where we've basically demonstrated this. So here's current obliquity of the moon. You can see lots of cold traps. Anything that's basically blue here is a place where water ice could potentially be stable. Now, we don't have the time scale over which the moon's obliquity evolved, because that depends on details of the dissipation in the Earth and stuff that are still being worked out. But we do know it certainly happened. As you increase the obliquity to 4, you can see the cold trap areas are decreasing and colder. And then right around 8, we get to a very interesting transition here. Now, Andy made the point that the coldest craters, as shown here, are the large flat-floored craters that have the least amount of scattered solar and infrared radiation at their centers. And that's true. And the smaller craters are, in fact, warmer in their interiors. But by about 8 or 12 degrees obliquity, you end up with a very different situation. Basically, now the sun has started to peer into these wide, flat craters, rendering them useless as cold traps. And then here we show the earliest cold traps, the ones that have been in effect the longest, and these turn out to be the sort of larger bowl-shaped craters. So it's very interesting that there's sort of this transition where the oldest cold traps are going to be the bowl-shaped craters, and then the wide, big craters that are the coldest today are more relative newcomers in terms of their cold trapping capability. So what I presented for you is sort of more or less stuff that's been shown in published papers. But there's a lot of new observations and new thinking coming along with regard to these cold traps on the moon. And one very important factor is this idea of sort of on what actual spatial scale they're on. We focused most of our efforts so far on, sort of large impact crater scale cold traps, sort of, on the order of 20 kilometers and stuff like that, because these are easy to quantify and model and deal with. But the moon is an airless body, and the soil has low thermal conductivity, and so it can support very, very large thermal gradients on relatively short distances. And the way radiation works is it's more or less independent of distance. And so there's a lot of effort ongoing with the Diviner data and other data sets to understand in detail what's going on finer and finer timescales. You can see in this high-resolution Diviner image, where we took this during the earliest part of the LRO mission, we had very low elevations over the south polar region, that there's a lot of detail to the thermal map. This is an actual thermal map shown in black and white. And you can see here that there's at every spatial scale, there's a lot of thermal variations. And the question is sort of, what does that really mean in terms of cold traps? Could you have a little micro cold trap behind a rock or a little rill? The LROC team on LRO, the imaging system, is now producing high-resolution views of some of these craters just looking in scattered light. They've figured out a way to tune their experiment and change their exposure to get views inside these craters. Here's the Faustini crater, and you can see here that there's a tremendous amount of stuff going on inside the crater in terms of illumination. And this is going to translate all the way down to fairly small spatial scales, probably even down to scales of meters. And so the question is, what could that mean in terms of the cold trapping capability of the lunar surface? Paul Hayne has actually done some work here where he's sort of taken a model where you just assume a statistically random distribution of slope angles and orientations and sort of calculated what fraction of the area as a function of latitude ought to be a cold trap based on that angular distribution. And notice that, basically when you get down to about 75 degrees latitude, you start creating all these micro habitats potentially for water, and their distribution increases as you go to lower and lower latitudes. And he suggested that this could be one explanation for what's going on with these neutron measurements, and that if you have a statistically increasing number of these little cold traps at higher and higher latitudes, these could then provide something of a signal that could be identified, for instance, by a very low spatial resolution instrument like a neutron spectrometer. So this is just one sort of dimension of the problem that needs to be taken into account. I might add, though, that any effort to land safely on the lunar surface, not just crash into it like Tony did, really needs to take into account this whole landing hazard issue. Basically the whole, and this, take it from someone who has a lot of experience with failed landings. The lunar surface is quite treacherous in this respect. In that it's basically, you just look at the lunar Apollo pictures, they're covered with these impact craters. And, if you don't have a, Neil Armstrong guiding you down to a safe spot on the surface, there's a pretty reasonable probability you would end up landing into, a relatively steep slope, 20-degree, 30-degree sort of impact crater scenario. And that's really tough. And these occur in these cold traps as well. So just be aware of that as you think about different mission scenarios. I wanted to spend the rest of the time I have right now talking mostly about Mercury, because for the case of Mercury, we have a very unusual situation where we have a bunch of different types of data sets that can be combined to tell a very coherent story, along with a thermal one for the thermal stability of volatiles. And this is a bunch of work that was published earlier this year in 3 papers in Science. And he talked about the radar results. He didn't show, though, these beautiful radar images that we have that were taken by Arecibo, which really show the impact craters at the poles of Mercury and their extremely bright radar signatures. And back in the 90s, I mean, we pretty much knew that this stuff was water ice for a variety of lines of evidence, including the early thermal modeling. But now with MESSENGER, with the ability to orbit the planet, to get topographic information, neutron information, and reflectance information all together, combined with thermal models, we have a really amazing airtight case. And this is, I think, important because it sort of shows, I think, a little bit how we could operate in terms of the moon, in terms of unraveling some of these issues, even though it's a very different sort of story. So first key piece of evidence comes from the MESSENGER neutron spectrometer, which basically flew close enough to these deposits to get a signal of neutron depression. And this is shown in the Lawrence et al. Paper. Basically, what you're showing is a simulated what the neutrons should have looked like had all these cold traps been composed of water, and then the red measurements are showing showing a similar trend. So we have essentially a neutron signature of the presence of hydrogen at the poles, which is very exciting. And then the MLA instrument provides two key pieces of information. MLA is the Mercury Laser Altimeter. It provides topography through measuring the speed, the time of flight of the laser pulses, as well as reflectance. And this is the first time we really got to look at one of these reflectance data sets. And Paul Lucy is going to talk about this at length at the next talk, so I won't belabor it. But suffice it to say that it makes a very objective normal reflectance measurement of the surface of Mercury. And the idea is to then start correlating this with the thermal results. And one of the key pieces of data they got was in this Prokofiev crater. It's around 85 degrees latitude. It's a big crater. And interestingly is when they got the first reflectance data inside the crater, they found very, very bright reflectivity. And this was probably the most exciting piece of data I've ever seen because it has the potential of confirming that a lot of the things that we really thought were true about how volatiles ought to work on these airless bodies were in fact true. So my contribution to this was to take the topography data, use thermal models to calculate the same types of quantities I've been describing on the moon, and then from this calculate the thermal stability of water ice in the very same way. Because it's so hot on Mercury, there aren't going to be these wild, large ground ice deposits, but inside the craters, we expect to find both surface and subsurface ice. We correlated the positions of the predicted water ice surface and subsurface deposits with the radar results, and it was essentially a perfect match. This green line here is what shows that. Temperature is along the x-axis, and this is the fraction of radar bright areas that have different temperatures, and basically there's a cliff right at 100 Kelvin, which means that surfaces that whose annual average temperatures are greater than 100 Kelvin are not radar bright, and surfaces that have temperatures that are lower than 100 Kelvin are radar bright. And this means basically that those radar bright signatures are due to the predominance of water ice. And this is also required to get the bright radar signals. And we know in Mercury that these deposits are, at least, a few meters thick. Okay, they're probably not like ice caps, like with like glaciers, but they're certainly, very, very substantial, clean deposits of ice. And what's so interesting about them is that their distribution appears to be very well organized. In other words, it's following the thermal patterns exactly, which is very interesting. And this shows some examples where we sort of zoomed in a couple regions here to try to sort of elucidate what's going on a little bit better. And I just wanted to show a couple of these plots here because you'll see a lot more of them later on. This is plotting annual average temperature as a function of radar brightness. And you can see here, again, all of the hotter areas are radar dark. And then as soon as you get into the areas that are less than 100 Kelvin, then you get a strong signal of increasing radar brightness. It's a beautiful result. And then this shows the reflectance of the MLA instrument. This is annual maximum temperature. You can't see it, it's just on the bottom here. And this is the MLA reflectance. And basically, this is sort of average Mercury. There's dark material surrounding these deposits, and then as soon as you get close to 100 Kelvin, then all of a sudden the MLA reflectance goes right up, indicating the presence of surface ice. And it's very exciting on Mercury because there's a lot of processes, as Andy described, that are going to tend to either destroy the ice or cover it up. And the fact that we see the ice on Mercury sitting there on the surface today, exactly where it's supposed to be thermally, means there must be a lot of processes that are delivering ice to the Mercury region, and that these are overpowering the various processes that are going to try to be destroying ice, of which there are many. I probably won't have time to show these, but these are a set of shots that were done at the press conferences that sort of illustrate this. And this is showing annual maximum temperature in the polar region, ice depth, and here's the MLA results that show both dark as well as some bright areas. These are off the main polar cap, but this is where we have the best data. And you can see these little bright patches here indicated by the arrows. Those turn out to be, if you keep your eye on those, exactly where the models predict that surface ice should be stable. Final thing I want to show, since the red light's on, is some of the most recent data we have from Messenger, where using the imaging system, now they've figured out how to image inside these permanently shadowed regions. And this is a composite of both illuminated as well as shadowed images of Prokofiev crater. And this was first shown by Nancy Chabot at the LPSC meeting this year. And they actually you can actually see the boundaries and the outlines of this ice deposit, the surface ice deposit inside this crater here, directly with the scattered light from the imaging observation. It's amazing. You know, this is the picture of the century as far as I'm concerned, because it really drives home the fact that these deposits are really there, and that they're bright, and that you can actually see them even though there's no direct illumination. You can also see the variations that exist within the deposits as well, and that's an important.
There's no terrain softening. It's not like a thick layer, right?
Yeah, it's just a relatively thin coating. But anyway, so with that, I think I'll close it down and turn it back to Paul.